Just a minute.
Okay, okay.
Yeah, now we can. Okay,
Yes,
now
sir.
you can go to next question, basically.
Yes, sir.
So,
The next question is that how we decide the how much element are present in our array. So, and I think you take a 324 element in all paper.
okay.
Yeah. So how we decide that? Because in a circular shape, circular array, we cannot be decide the how much element are fit in this.
Oh, so is it in center fed or this one?
Yes, only center fit only.
Okay. So center fed, you can just check, right? Like, in the so you want to check what Ajay, in the simulation tool you have to check so how many elements are got eliminated, right? Correct?
Yes, sir. Yeah.
Okay.
And sir, what we take the space, whoa, element spacing between them.
Element spacing. Yeah, element spacing.
Yes,
See,
sir.
the thing is, yeah, see, the thing is, spacing. In general, we used to keep um, in general, we used to keep uh, 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 which used to keep a 0.5 lambda, right? 0.5 lambda, 0.7
Point
lambda
five
also you can
lambda.
keep. Yeah, yeah. That also again depends on the gain that you are expecting and how many elements you are planning for the array. That all that stuff.
Yes. So, but we take the all element have a same fixed center. Mean all element have a same center. Yeah, it will be depend on the space element. I think
Sorry.
can I share, sir? Can I share my screen so I show the diagram?
Yeah, 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 yeah. That will be better
Yeah.
actually.
Yes, sir. Because yeah, yes, sir. Can you see?
Yeah, yeah. 1 minute actually. Coming up, but internet is a bit slow actually. Basically.
Yeah, yes, no problems.
Yeah, it's coming. Yes, 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 yes,
Yeah.
yes.
Actually, my question is that.
Uh-huh, uh-huh.
Yes, sir. Yeah. So my question is that we have taken a circular reflectory. So we have taken this point is our center and number of element are placed. Yeah, we take a rectangle. So we will adjust that. So this is the center point, and we take all the like first element is on center, and like this element is 15 mm, and another element is also this element is have a 0 0 center position 0 0, and another element have a position of 0 comma 15. Yes, sir.
Okay, 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 okay.
Yeah, 0
Uh-huh.
comma 15, and so many so thing. So the spacing element is also in this element. If the both the element have a same size, then spacing element is 0. But we can take according to the phase difference. So the
No, no,
phase
no, no,
element
no.
is
The thing
different.
is, remember, inter element spacing is always inter-element spacing, center to center.
So, but both element have a same center, sir. The same center not mean the difference between them is 15 mm. All the element have a
Okay,
difference
okay.
between the
So you
15
meant
mm.
to say, see, for example, you are saying that, for example, I have one element is, for example, 15 by 15 mm. Okay.
Yes, sir. Yes,
But
sir.
same same element I am going to place in next to it. So what you are saying is, if I am
Sir,
keeping my element
yes, sir.
size actually lambda by 2, right? So if I am
Yes, sir. Yes,
keeping
sir.
the same element next to me, then again it will overlap. That's what you are saying, right? Actually.
Sir, it is overlap, but both the element have a different size. So we take the center is exact lambda by 2.
Okay.
Yeah, because the in this element have a different phase difference, and this element have a different phase difference. Actually, PP, that is the progression phase. And what I say, mm, PP is the what phase difference is saying. Special phase delay and is another thing to think. Yes, a progressive phase constant. Progressive phase is different, 5 pp. So this element have a 5 pp difference and this element have a 5 pp difference. So both the element have a different size actually. So we cannot be take the center of lambda by 2 in between two elements.
Okay.
Yes, sir.
Mm,
So my question is understand here? Yeah, another.
yeah, I'm trying to cover. Actually, can you come again, please? Sorry, yeah.
Yes, sir.
Can you come again, please?
Question again?
No, no, no.
Yes, sir. Yeah.
I can see the screen, but only just a question. Can you come again with the question, please?
Yes, sir. Yeah, yeah. Question. I again the question. So
Question,
stop the
question.
share.
No, no, no. Sharing. I can see your screen. Can you
Yeah, yeah, sir.
again
Yeah,
tell me? Yeah.
yeah, yes, sir. Sir, actually, we have a rectangle shape
Okay.
reflectory. Okay.
Okay. Okay.
So in this reflectory, we have a center. This is a symmetrical portion. So
Exactly.
yeah, the our first element is placed over here, 0,
No, 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 no.
0.
Not there. Not there. Not there. In the
Yeah,
first quadrant. First quadrant. Go to first quadrant.
yeah,
Let
the
me
first
take control.
quarter.
Yeah. Let me take control. Let me request for control.
Yeah.
Just a minute. Where is that request control? Uh, hmm. There should be some control basically. Okay, usually some control will be there usually. Okay, yeah, that's fine. Okay, okay, yeah, yeah. You have to go to first quadrant and then you
Yes,
have
sir.
to
Here is the first quarter.
yes. First
So
quadrant. Yeah,
can you mitigate? Yes.
yeah. Please go ahead. Please go ahead. Yes.
Yes, sir. This is the first quarter. Yes.
Okay, yeah. First quadrant. In that you have to start your element basically.
Here is the.
No. Okay, shall I share my screen? Tell you
Yes, sir. Yes, sir.
what?
Yes, sir.
Just a
I
moment.
stop here.
Yeah,
Stop.
please. So now you are having problem in element location, right?
Yes,
Correct?
sir. Yes, sir. Main location
Okay.
is there, and I am
Okay.
also calculate the different formulas, but
See,
getting the face position, but not be allocate the location.
okay. Okay. So let me tell you from the unit cell perspective and also the array element perspective. So unit cell
Yes.
perspective, see, you are having some element size, right? Including
Yes.
substrate and ground plane. Okay. This
Yes,
size,
sir.
for example, you will simulate the unit cell, right? This
Yes, sir.
size should be lambda by 2.
Yes, sir. Yes.
This size, not the patch size, basically.
No, no, sir. Yeah, this is it's substrate size.
Yeah. So lambda by 2 is the patch size will never be lambda by 2, the patch size, only the unit cell size. So this is
Yes,
what
sir.
you are keeping it as, interelement spacing. So what you will do, you have this is the x, let's say y axis. This is let's say x axis. Okay. Now
Yes, sir.
see, you have an array, means array of size this much. Okay. Now you have to place
Yes.
the element, right? First
Yes.
element you have to keep like this. Okay, the second element and so on. Okay, and the left you have to take a mirror image. Okay,
Yes, sir.
for
Yes.
example, okay, if it is a symmetrical array, right, you will have one element here, one element here, one element here. So all four will be same if you are having symmetrical structure. Okay,
Yes.
okay, so four element will be same.
Sir.
That's it.
Yes, sir.
Okay, see this element spacing, right? This is 0. This element space, the spacing between these two will be For example, if you are taking 10 gigahertz, 10 gig, so lambda by 2 is what?
Lambda by 2,
15,
15,
15
sir.
mm, 15 mm.
Yes, sir.
So 15 mm will be there. If you take the
15.
interlement spacing between these two, again 15 mm. If you take interlement spacing between these two, again 15 mm. Similarly, here also. This is for the case, especially for center fed, center fed reflector array, which
Yes,
means
sir.
center fed means this one. Okay, you are here. This is the feed location basically, center fed
Okay.
reflector array, and this is only for that. But if you are going for offset fed, what happens? See, this element will be different, this element will be different, this element will be different, this element will be different. Okay,
Yes, sir.
but you can put any element that you want. It can be of any size. But the only thing is you have to maintain the interelement spacing is same. Okay, so in this way
Okay.
only you have to plan basically.
Okay, sir. Okay.
Okay, you have to first quadrant, no, you have to separate, and then for example, you have to place element. For example, in the parameter you defined right in the CST you defined right. There you have to keep, for example, you can create a variable called spacing underscore x. Okay, one variable and spacing underscore y like that. Okay, then you can
Yes.
put what you can do is you can just place just y by 2 and x by 2 location. You can mark it as a center, then accordingly you can place an element, means you can
Yes.
draw the patch size basically.
Yes, sir. Yes, sir.
Yeah, that way you can plan. And for circular
Oh,
thing, right, circular thing, I think if you want, I can, let me find out. I have some MATLAB code actually, how to find the element and how to place that and all.
yes.
I will send. Okay,
Okay.
I will send you the MATLAB code. Okay,
Okay,
for
okay,
circular
okay, sir. Okay.
how many element will be there like that.
Okay, okay, sir. No.
It's very easy only. So only thing is, see, the thing is in circular, no, how many elements will be there? That will be decided upon this one, right? So you keep on increasing this one, means one by one you count. Then you will see the boundary as this one. So if you
Yes,
see
sir.
boundary, then it will not be element will not be placed. Accordingly, this will
Yes.
vary. Yeah.
Yes, sir. Yes, sir. Okay,
So long
sir.
back, I did some MATLAB code also. How to find out number of elements can be fit in for a given reflector, circular reflector.
Okay, sir.
Anyway, tomorrow I
And
will try to find out and then send it to you. Yeah, yeah.
okay, okay, sir. I find out. And sir, yes, sir. I got it this point. And sir, can we actually I getting the some location. So some location we getting I getting the face what element having this face. So
Yeah,
so the this face is interpolate with the our unit cell result.
exactly.
Yes, sir. So can I share my screen, sir? I show my
Yeah,
Excel file actually.
yeah.
Yes, sir.
Don't call me sir. You can call me Linga. It's fine. Okay.
No, no, sir. You
No,
are
no,
sir.
no.
Actually.
No, no, not
Yeah.
like that. Yes,
No,
see,
no,
you are a
sir.
professional,
And
right?
I respect you, sir.
No, no, see, if you call me Linga also, it's a respect only. Don't worry. Okay.
No,
There are
yes, sir.
humans.
So
Yeah.
yes, yes. Here is my screen, sir.
Yeah, I can see your
Yeah.
screen.
So actually, I am taking the render. I am taking the xi, and here is the my face center point 200
Okay.
mm, and xi is zero position, y is the zero position, and I calculate the some position OA and FA and FA minus FO, and I calculate the this face center is 0 0 comma. Then I getting the face is 0 and 15
Okay.
15 comma. Then I getting the 13.46 degree phase, and
Hmm.
another is 30 mm, then I getting the 53.40. But
Okay.
when the phase when the center position is increasing, then our phase is increasing the 1200 and 1400 and 600. So
Exactly.
and we have taking the only the unit cell have a minus 180 to 180 degree phase.
Mm-hmm.
So how we interpolate this point, sir?
Exactly. Okay. Let me share my screen. Okay.
Yes, sir.
Shall I share my screen?
Yes, sir.
I got your point. Okay.
Yes. Actually, I want to design a reflector without any code, sir. So
Yeah. Okay. Okay. Fine. Fine. I got your point. Okay. The thing is, you are saying that, see, you are having this. If you go offset like this, feed offset like this, correct? Your
yes,
feed position was here, 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 like that, right?
yeah,
Right?
yeah,
Correct? Okay.
yes,
So now, okay. So let's say one point here. Okay. Let's say one point. We take this one point in the reflector. This is the feed location. Now, what is the
yeah.
length?
F by D. Yeah,
No, no,
yeah.
just generally length.
F. Length is
For example, let's say
200. I
X,
take I take 200, sir.
200.
200
It's
mm.
okay.
Yeah, yeah,
X, X,
yeah,
X. Okay. When you go
yeah,
here, it will be X plus something, right? The
yeah,
length.
yeah. Explore D by cos theta, D by anything.
Similarly, X plus something. Okay.
Yes,
Correct?
yeah,
Okay.
yeah.
So, these phases are how it is calculated is very simple. You have to multiply with the K naught into length.
10
K
into
naught
L
is
length.
what?
Yes.
2 pi
K naught
by
is phase lambda.
2 pi by lambda, right?
Yeah.
Pi by lambda. So now, so how do I calculate the phase? Length, let's say it is a x lambda, let's say x is equivalent to some y lambda, let's say, okay, some
Yeah.
y lambda. Okay, so I have to substitute this value y
Lambda.
lambda, right? So lambda get cancelled, then I will get a value of 2 pi into y.
Y.
Okay. Similarly, for the other case also it will be 2 pi into y plus something, right? Y plus 2 pi of y plus something, right? Accordingly, the
Yeah.
phase will be calculated. That's how it is
Yeah.
calculated for in your case also. Okay. So now
Sir,
see how
excuse me, sir.
sorry.
Sir, can you repeat the Y lambda is what, sir?
See, y lambda is like, see, for example, x length is there, right? This is the length,
Yeah,
right? 200
excellent is
mm.
there. Yeah,
The 200 mm, let's say 200 mm. Okay.
yeah,
Let's say your wavelength, let's say you are operating in frequency of, for example, 10 gigahertz. Okay. So what is the lambda
yeah.
for at this point? It is
15
30
mm.
mm is the lambda,
Yeah,
right?
30 mm. Sorry. Yeah.
Okay. Let's say 30 mm is lambda. If you calculate, see, this is the free space wavelength, right? For 10 gigahertz,
Yes, sir.
30 mm is free space wavelength. So what is free space wavelength?
Yeah.
Lambda is equal to C
C by
C
F, sir.
divided by F. So C
Yeah.
is what? Free space velocity. Correct?
Yes.
But
Yeah.
we actually how we calculate? We have to calculate lambda G, guided wavelength, right? Correct?
Yeah.
So how do you calculate guided wavelength? Lambda naught divided by square root of epsilon r.
Epsilon.
Correct?
Yes,
So
sir.
how this concept comes? See, where wave propagating. If it is in free space, it will have a certain velocity. But
Yeah.
when it find a medium with some certain epsilon r more than one, then what happens?
Yes, sir.
Then
It will be divided by.
your speed will go down, right? By
Yes, sir.
this fact, square root of epsilon r. That's what we are saying. Okay. So, for
Yes, sir.
example, analogy, similar analogies. For example, see, you are going in a vehicle, okay, a bike, in a perfect, a road, okay. You are going
Yeah.
in certain speed, 80 km speed. Suddenly,
Yeah.
you see, there is a lot of sand is there. You have to drop down, right? You are entering into different medium, right? You have to slow down. Then you have to go slowly, right?
Yeah, yes,
That's
sir.
the
Yeah.
same analogy. Okay. Now, this is
Yeah.
the guided wavelength. Okay. So now, let's say guided wavelength of this case is, let's say, for example, 20, 28, 20, 20 mm, let's say, 20 mm. Okay. Let's take 20
Yeah.
mm. So now, 200 mm was the length, right? Okay. So now,
Yeah.
lambda g is 20 mm. So how many lambda I have? 10 lambda, right?
Yeah.
The total length is, if you are representing in terms of lambda, it is 10 lambda.
10
Correct?
lambda.
Okay.
Yeah.
So 10 lambda, right? So now this instead of yx, right, y lambda, right, I'm using tan lambda.
Yeah.
Okay. So lambda get cancelled. So 10 into 2 pi, it will be,
25.
6.24, 61.24, like that it will come. Correct?
Yeah. Yes, sir.
61.24. Oh, sorry, that is in radian, right? Now you have to convert back to
Yeah,
uh,
radian, yeah.
then it will be around 180-degree. If you multiply, it will go more than something. See, for example, 200 lambda. How many lambda are there? 10 lambda, right? Which
10
means
lambda.
approximately 3600 degree. So 1 lambda corresponds to 360 degree, right?
Yeah.
Correct? 1
Yes,
lambda
sir.
corresponds to 360 degree. So
Yeah.
quarter lambda corresponds to 90 degree. Half lambda corresponds to 180 degree. One full
180.
lambda corresponds to 360 degree. Okay.
360 degree.
Okay.
Yeah.
So now, if you are multiplying in terms of lambda, which means, see, if the length is in terms of lambda, you are indirectly what you are doing? 6 into, for example, 6 lambda means 6 into 360 degree. So it is always going to be the multiples of 360 degree or whatever it may be. Okay. So now you are saying that I have a unit cell is offering minus 180 to plus 180, right?
180. Yes, sir.
Plus 180 degree.
Yes.
Degree. But so how can I write this? It's also a minus. You can write, wrap this phase to. In one of my video, I have explained how to convert this into 0 to 360 degree. Correct? 0
Yes.
to 360. All are one and the same. It's only the about the wrapping, phase wrapping. Okay. So instead of
Yeah.
minus 180, what I will do, I will add 360. Then you will get the 0 to 360 degree value. Okay. Correct?
0 to 360. Okay.
360.
Okay.
Okay. Now,
Yeah.
so this is the one way of doing your element side. Element phase side, you have to do this unwrapping, wrapping and unwrapping. Okay.
Yeah.
Phase wrapping, phase wrapping. Nowadays, CST also has that inbuilt. So you just click on
Yeah.
the
Yeah.
phase unwrap, then it will unwrap. Okay.
Yeah, sir.
Now,
I see your
coming back,
video.
this is about element one. This is next coming back to this one. You are getting 3600 degrees, for example. Okay. So now,
Yeah.
so what you have to do? You have to wrap this face for 360 degree. Whatever element is giving. For example, if your element is giving for 320, you have to wrap that face for 320 degree. Total phase I'm telling. See, for example, you are
Yeah.
you see this is the wrapped one. If you unwrap it, let's say 0 to maximum value is 320 degree. Let's say, okay, maximum value is
Yeah.
320 degree.
Great one.
So now what you have to do? You have to wrap this face according to 320 degree. Wrap
Yeah.
this face according to 320 degree.
Great one.
Because your element can offer maximum of 320 degree. That's all right. It cannot offer more than that. So see in the tool also, it actually it is offering maybe more than 360 degree, but it is wrapping that one. Okay. So
Okay.
then what you have to do in 360 3600, how many 360 320 degrees are there? Then you have to see the only thing is that let me tell you one thing. Only thing is that see whether you are wrapping for 320 degree, whether you are wrapping for 400 degree, doesn't matter. Okay. Okay. But
Yes,
obviously,
sir.
the phase to be compensated is in terms of thousands. Okay. What you are doing, you are only convert that into wrapping basically. So here what you are ideally doing, see what we have to see. See, let's say this is the reflector ray. You are having, this for some length is there. This some length is there. This some length is there. Okay. Let's say this is 3000. See, let's say 3x degree, y degree, z degree. Okay. So
Yeah.
let's say this is 3000. This is 3200. This is the 3400. So
Yeah.
now what you have to concentrate is, see, your element should offer, for example, if this element is offering 0 degree, for example, okay, this element
Yeah.
should offer the difference 200 degree. That's it. That's what I should think.
Yeah.
Got your point? Here, this element should offer 400 degree. It's
400.
actually a relative phase difference. That's all. Okay. It can be 3000 degree, 8000 degree, whatever it may, no problem. Okay. The only thing is that, see, relatively, this length is having 3000 degree, this length is having 3200 degree. I have to compensate for that 200 degree only. That's all.
Yes.
It's a relative phase between the elements, not the length basically. There are two ways to look at it. One is simply compensating the length. It means overall length. See, my element will offer this degree. This element, this element will offer this degree. This element. That is one way to look at it. The other one is simply compensating for the difference. So this will
Yes.
offer 0 degree for that incoming signal. This will offer 200 degrees for that incoming signal. That's it. So what it does
Yeah.
is, you have this. You are having incoming signal gets reflected. So while getting reflected, no, it will add this phase. That's all.
Yes.
So
Yes.
that all get normalized. So all, it's going to be complementary, right? Minus 200. So that it will get nullified, and all delay is getting compensated.
Okay.
If you go in further details in physics, okay. So phase
Yeah.
is
Yeah. I see the ray theory. Actually.
yeah, phase physics, right? So phase is actually a delay. Okay, phase is another parameter is delay. Correct?
Yeah.
Phase, how I am saying, this is the, okay. So now see, this is the 360 degree, right? Total 360 degree. Now what I am doing, see, if I am delay of, for example, 1 lambda, delay of 1 lambda,
One
let's say,
lambda.
which means 360 degree corresponds to 360 degree, right? If I am
Yeah.
delay of for an, quarter lambda, it is corresponds to 90 degree, correct?
90 degree.
90 degree
Yeah.
phase shift. Or you can see, for example, one signal, 1 lambda, it takes 1 second to reach there. For example, 1 second to reach some location, means some array location. But if you are
Yeah.
having, next path, you are having one path is reaching in this location by 1 lambda. The other, in this one, it is reaching by 1.5 lambda.
Yeah.
Let's say,
Yeah.
okay, the path length is 1.5 lambda. Here, this is reaching in 1 second. This is going to be reaching in 1.5 second, right?
5 seconds. Yes.
So this 0.5 second is the delay, correct? Okay. What I have to do,
Yeah.
I have to introduce a delay over here, okay, in order
Yeah.
to get that compensated. I have to see while reflecting back, no, this has to go as it is. Here, what I have to do, I have to introduce a delay that causes, that introduce 0.5 seconds delay. Okay.
Yeah.
In other words, we can say phase. That is what is
Yes.
happening.
Yes.
So in reflector, you should be very careful about the terms: delay,
Yeah.
phase, compensation, and matching. Sorry, everything is close related basically.
Yeah. Sir,
Yes.
yes.
I hope you got something basically.
Yes, sir. Yeah, I got it. I got it. Everything, sir. And yes, sir. So, what I say?
I will share with you these videos also. Okay.
Yes.
So just
Yes,
go
sir.
through it,
Yeah.
and
Yeah.
then yeah.
Yes, sir.
If you have any doubt, you can contact me anytime. No problem. Okay.
Yes, sir. Okay. Okay. And thank you, sir. Thank you
Some of
very
the
much.
things I could not recollect, but because it's
No,
almost
no, no.
3 years now. But it's
Yeah,
okay.
yes, sir.
No problem. Yes,
Yeah,
sir.
at the
Now.
time you are working the HTL.
Yeah.
Yeah, HTL. Okay.
Okay. So that's all.
Yes, sir. That's all. Can I share
Yeah.
my screen, sir?
Yeah, please.
Yeah.
Yeah.
Sir, so I think yeah, this is a horn antenna. I designed the horn antenna. So
Yes.
how we measure the H pattern or E pattern, sir?
Go to 2D, 1D, 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 1D,
One
1D polar. Polar or Cartesian, it's fine.
polar.
Yeah.
Yeah.
This is the one. Okay. So can
Yes.
you go to see this E plane and H plane, right? I think this
Yes,
is
sir.
circular horn, right? Actually,
Yes, sir.
circular horn. If it is symmetric, go
Yes,
to
sir. It
far
is
field plot.
symmetry.
Go to far field plot. Yeah, here you can see cut angle is there, right? Cut angle, cut angle, cut
Rectangle.
angle on the right. Cut angle, cut
Yes,
angle.
sir. Yeah.
Okay, zero, put zero.
You know,
Yeah, enter,
and
enter.
yes, sir.
Yeah, both are
Enter. I.
same because you are getting same pattern, right? Because it's a symmetric pattern. Usually
Yes.
conical horn and circular horn will have a symmetric pattern in all the cut, right? That's what.
Yes.
5 0. See, usually what we'll do is in pyramidal horn, no. If you are
Yeah.
see if your width is along x-axis, let's say in pyramidal horn width is along x-axis, height is along y-axis. If it is like that,
Yeah.
then if you are
Yeah.
taking 0 degree means that is corresponds to H plane, and 90 degree corresponds to E plane.
Okay. Okay, sir.
Okay, that's all. First,
Okay.
whenever you get confused, no, that just go to pyramidal horn. Okay, pyramidal
Okay, sir.
horn.
I got.
Because along a width, you will have a H plane. Along a height, you will have a E plane.
E
That's all.
plane. Okay.
Here it will be
Uh,
same. That's why you are getting confused.
okay, sir. No problem. And sir, other thing is that when I take the different diameter, then this S11 parameter is minus 17 dB. But
Yeah, it
when
will
we
vary.
yes, sir, it is very. But when I operate this reflectory, then it will
Mm.
get very low, sir. So why this problem, sir?
Yes. See, this is what matching. The feed location problem. Okay. See, feed
Yeah,
location not only see what it does is, see, you have to match that, right? What happening? See, when you are in wrong feed location, what will happen is it will it will see, it is getting reflected, right? And it is
yes, sir.
disturbing the matching of your horn antenna as well.
Yes, sir.
That's why it is, you have to match the location and feed position.
Oh,
You have to match.
oh,
I have, I did a lot of measurements. Just moving this feed horn, doing the measurement. See,
yeah.
simulation is somewhat easy. You can just
Yes, sir.
move here and there. But when you are designing the horn, right, means location, right, that time you have to move here and there. I did so many things, iterations basically. Finally,
Yes,
you
sir.
have to lock it. We don't have a mechanical facility also that time. What we'll do is we'll finalize the location, then we'll go for mechanical mounting structure and everything. So that way
Yes,
you have to do. Okay, that is actually basically, how do you measure? See, before we go for radiation pattern measurement, right? What we need to do
yes,
is we have to see the theoretical. It means the simulation feed on location will be different from measurement one. Measurement will be different from feed the simulation, because first you have to optimize the matching by moving
yes,
here and
sir.
there. Once you are getting perfect matching throughout the band, what you are looking for, then you have to go for, you log the location and then make the mounting structure properly and then everything. Then you go for this measurement, radiation pattern measurement, basically.
Okay, sir.
That's how we go. Okay.
Okay, sir. I got it.
Yeah.
Okay. Thank you, sir. Thank you.
But you will learn a lot of things. That's the one. That's for sure.
Okay. Okay, sir.
Thank you. Thank you so much. Yeah, if you need any other help, right? Feel free to get in touch
Yes,
with
sir.
you. I'm sorry because so many,
No,
due
sir.
to some
No
work,
problem.
so
No.
I could not able to
Yeah.
uh, help you.
So
But
the
so
and you can say you send the MATLAB code, sir. Actually, I
yeah,
have the MATLAB code.
I
I
will send
also
you.
have the MATLAB code, and this is this type of GUI, and
Yeah.
yeah.
It's good. Actually. It's you are getting right this one.
Yes, sir. But how much element is so you can send the code, sir.
Yeah. I will try to find out that because I long
Okay,
back I did that because I also
okay, sir.
struggled
No,
with this
no.
one. I
Okay,
have to
okay, sir.
learn
No
this.
problem, no problem, no problem. Thank you, sir. Thank you very much,
Thanks.
sir.
Yeah, welcome. No problem. Okay.
Okay, okay,
Okay.
okay,
Thank you. Thank you so much. Bye. Bye.
okay. Yeah, bye,
Good night.
bye. Thank you. Good night, sir.